In 2021, the U.S. Navy deliberately subjected the USS Gerald R. to explosive shocks equivalent to 3.9 magnitude earthquakes. These shock trials were designed to test the ship's resilience to combat scenarios. But how do these controlled tests compare to the unpredictable fury of a real-world deadly storm? In this video, we'll analyze the data from both events to understand the true limits of the world's largest aircraft carrier. Naval engineering has undergone a remarkable transformation since the age of wooden ships. In the past, vessels were built primarily with timber, relying on the skill of craftsmen and rudimentary understanding of hydrodynamics. Today's naval architects employ advanced computer simulations and material science to create ships that can withstand extreme conditions. Large vessels face significant challenges in turbulent seas. The sheer size of modern ships, while providing stability in calm waters, can become a liability when confronted with massive waves and powerful winds. As climate change intensifies, these challenges are becoming more frequent and severe. Recent data indicates a 30% increase in the occurrence of extreme weather events at sea over the past decade, putting additional stress on naval engineering. To combat these growing threats, naval engineers have made substantial advancements in hull design and materials. Modern hulls are now crafted using high-strength steel alloys and composite materials that offer superior strength-to-weight ratios compared to traditional steel. These materials allow for more flexible designs that can better absorb and distribute the forces exerted by violent seas. The USS Gerald R. represents the pinnacle of these engineering innovations. Its hull incorporates a unique blend of high-tensile steel and advanced composites, resulting in a structure that is both lighter and stronger than its predecessors. The carrier's bow flare has been optimized through extensive computational fluid dynamics modeling, allowing it to cut through waves more efficiently and reduce the impact of heavy seas on the flight deck. One of the most intriguing features of the Ford-class carriers is the implementation of a bulbous bow. This underwater protrusion alters the way water flows around the hull, reducing drag and improving fuel efficiency. More importantly, it helps to dampen pitch motions in rough seas, enhancing the ship's stability during flight operations. The ship's innovative structural design extends beyond its exterior. Internal compartmentalization has been refined, with watertight sections distributed more effectively throughout the vessel. This not only improves survivability in combat situations, but also enhances the ship's ability to maintain stability in extreme weather conditions. As we examine these advancements, it's natural to wonder how they translate to real-world performance. Initial reports from sea trials suggest that the USS Gerald R. exhibits superior stability compared to its Nimitz-class predecessors. The ship has demonstrated the ability to maintain flight operations in sea states that would have forced other carriers to suspend activities. However, the true test of these engineering marvels lies in their ability to withstand nature's most powerful forces. While passive design elements significantly improve a ship's resilience, they are only part of the equation. To truly understand how the USS Gerald R. can withstand a deadly storm, we must next explore the realm of active stabilization systems, which work in concert with these structural innovations to keep the ship steady in the face of nature's fury. As waves crash against its hull, the USS Gerald R. remains steady, defying the very forces that once dominated seafaring vessels. But what hidden technologies allow this behemoth to stand its ground against the ocean's fury? The answer lies in a sophisticated dance between ship and sea, orchestrated by systems that are anything but passive. Active stabilization systems represent a significant leap forward in naval engineering. These systems work in real time to counteract the forces of wind and waves, maintaining the ship's stability in even the most challenging conditions. At the heart of this technology are two primary components: fin stabilizers and gyroscopic systems. Fin stabilizers function like wings beneath the water's surface. These large, movable blades extend from the ship's hull and rotate based on the direction and strength of the waves. As the ship begins to roll, the fins adjust their angle, generating forces that oppose the motion. This significantly reduces both transverse and longitudinal rocking, even in challenging sea conditions. Gyroscopic stabilizers, on the other hand, operate on the principle of conservation of angular momentum. These massive spinning wheels, similar in function to the tires of a bicycle, generate a powerful stabilizing force when the ship begins to roll. The gyroscopic effect helps keep the ship level, providing additional support against capsizing in turbulent waters. While passive stabilization methods, such as hull design and weight distribution, provide a solid foundation for ship stability, they have limitations. In extreme weather conditions, these passive systems may not be sufficient to maintain the level of stability required for safe operations. This is where active stabilization systems truly shine. The USS Gerald R. Ford incorporates some of the most advanced active stabilization technologies available. The ship's computer systems receive real-time information about its position from onboard gyroscopes. This data is then used to make precise adjustments to the stabilization systems, ensuring optimal performance in any sea state. The effectiveness of these systems was put to the test during a 2022 training exercise. The USS Gerald R. Ford encountered significant rolling due to high waves, conditions that would have challenged even the most seasoned sailors. Despite the tumultuous seas, the carrier's structure withstood the loads without sustaining damage to the aircraft on board, a testament to the power of its active stabilization systems. As we consider the real-world performance of these technologies, it's clear that they represent a significant advancement in maritime safety and operational capability. The integration of fin stabilizers and gyroscopic systems exemplifies the U.S. Navy's commitment to enhancing ship effectiveness in harsh environments. However, even the most advanced stabilization systems cannot entirely negate the impact of severe weather. To truly understand how the USS Gerald R. Ford navigates deadly storms, we must next explore the critical role of advanced weather forecasting in naval operations. These predictive technologies work hand in hand with active stabilization systems, allowing ships to anticipate and prepare for nature's most formidable challenges. Imagine having a crystal ball that could show you every storm brewing on the horizon. For the U.S. Navy, this isn't science fiction, it's a daily reality. But how do they achieve this level of foresight, and what happens when their predictions are off? Weather prediction has always been crucial for naval operations, but traditional methods were limited. In the past, sailors relied on barometers, wind observations, and cloud patterns to forecast weather conditions. These techniques, while useful for short-term predictions, often fell short when it came to anticipating severe storms or long-term weather patterns across vast ocean expanses. The challenges of accurate maritime weather prediction are numerous. Oceans cover more than 70% of the Earth's surface, with limited ground-based weather stations. Rapidly changing atmospheric conditions, complex ocean-atmosphere interactions, and the sheer scale of global weather systems make long-term forecasting a daunting task. To overcome these challenges, the U.S. Navy employs a suite of advanced meteorological technologies. At the forefront are polar orbiting weather satellites, which provide comprehensive data on clouds, air and water temperatures, currents, dust storms, and ice coverage. These satellites offer a bird's-eye view of weather patterns over large areas, enabling more accurate predictions. Complementing the satellite network is a global array of over 1,000 weather buoys. These floating sentinels measure winds, waves, barometric pressure, and air and sea temperatures. The data they provide is particularly crucial for assessing hurricane formation and tracking storm centers, offering valuable insights into the most dangerous weather phenomena at sea. The Navy integrates this wealth of data into powerful environmental models, such as the Joint Typhoon Warning Center models and Wave Watch 3. These sophisticated systems create accurate representations of the environment, allowing for precise weather condition predictions. But how does all this data translate into real-time navigation decisions? Every U.S. Navy ship is equipped with onboard weather instruments, including anemometers, barometers, and weather radars. This allows for constant monitoring of local conditions, which can be cross-referenced with the broader forecasts provided by the Navy's global systems. The integration of advanced weather forecasting with navigation technologies enables U.S. Navy ships to optimize their routes continuously. By planning alternative paths to avoid areas with high waves, strong currents, or adverse weather, the Navy significantly reduces the risk of instability or capsizing. This proactive approach to weather forecasting and route planning has proven critical in preventing potential disasters at sea. The ability to make timely adjustments based on accurate predictions has undoubtedly saved lives and protected valuable assets. As we consider the USS Gerald R. Ford's ability to withstand deadly storms, it's clear that advanced weather forecasting plays a crucial role. However, even the most sophisticated technology is only as effective as the crew operating it. In our next section, we'll explore how the Navy prepares its personnel to make split-second decisions in the face of nature's most formidable challenges. When faced with a raging storm at sea, even the most advanced aircraft carrier is only as strong as its weakest crew member. The U.S. Navy understands this critical truth, investing heavily in comprehensive training programs designed to forge unbreakable teams. But what exactly does it take to prepare for the unthinkable, and how do these drills translate to real-world emergencies? The crew of the USS Gerald R. Ford undergoes rigorous and extensive training to prepare for harsh weather conditions, ensuring they know exactly what to do in emergencies. This training encompasses a wide range of scenarios, from routine operations to extreme situations that could potentially lead to catastrophic outcomes. Regular drills form the backbone of this preparation, with a particular focus on damage control exercises. Damage control drills are designed to simulate emergency situations that may lead to capsizing or sinking. These exercises train crew members to respond quickly and effectively to flooding or structural damage, honing their skills in containment, repair, and evacuation procedures. The unpredictable nature of emergencies at sea necessitates this level of preparation, as a single mistake or delayed response could have dire consequences. Evacuation drills represent another critical component of the crew's training regimen. These exercises prepare personnel for the worst-case scenario, safely abandoning ship. Crew members practice launching lifeboats, gathering essential survival equipment, and coordinating large-scale evacuations under simulated emergency conditions. This training ensures that even in the most chaotic situations, the crew can execute a swift and organized departure from the vessel. Man-overboard drills are particularly relevant when considering the challenges posed by extreme weather. These exercises train the crew to execute a swift and organized rescue operation if a crew member falls overboard during rough seas. The drills emphasize effective communication and coordination, skills that become even more critical when battling against turbulent waters and high winds. The U.S. Navy's commitment to crew training is evident in the regular conduct of these drills, which equip sailors with the skills necessary to navigate through the toughest situations at sea. This emphasis on preparedness extends beyond physical actions to include decision-making protocols during storms. Crew members are trained to maintain a vigilant watch and continuously monitor weather forecasts and sea conditions, allowing them to anticipate and respond to changing circumstances proactively. The techniques learned during training could make the difference between life and death, as crew members develop keen observation and decisive decision-making skills that determine the fate of the ship. Expert opinions highlight that these human factors, including crew training and decision-making, are crucial for maintaining ship safety, especially in unpredictable maritime environments. As we consider the multifaceted approach to safety aboard the USS Gerald R. Ford, it becomes clear that the synergy between advanced technology and highly trained personnel forms a formidable defense against nature's most powerful forces. This combination of cutting-edge engineering and human expertise represents the forefront of naval resilience, setting new standards for maritime safety in an era of increasingly unpredictable weather patterns. The USS Gerald R. Ford's resilience in deadly storms stems from a combination of advanced engineering, active stabilization systems, and rigorous crew training. Its innovative hull design, incorporating high-strength materials and optimized hydrodynamics, provides a solid foundation for stability. The integration of fin stabilizers and gyroscopic systems actively counteracts the forces of wind and waves, maintaining the ship's equilibrium in challenging conditions. Looking to the future, naval engineering is poised for further advancements. Research into adaptive hull surfaces and artificial intelligence-driven stability systems promises to enhance the safety and operational effectiveness of vessels like the USS Gerald R. Ford. These technologies may allow ships to dynamically adjust their shape based on sea conditions and utilize real-time data analysis to prevent capsizing scenarios. The importance of continued innovation in maritime technology cannot be overstated. With approximately 50,000 U.S. Navy sailors deployed globally aboard around 100 ships, ensuring their safety and operational readiness is paramount. As climate change intensifies and extreme weather events become more frequent, the need for robust and adaptable naval vessels will only grow. The ongoing development of cutting-edge technologies in naval engineering will be crucial in meeting these challenges and maintaining maritime superiority in an increasingly unpredictable world.